Okay, so thanks, Adrian, for the introduction, and thanks for inviting me to give this seminar today. So good afternoon, everyone. So today I will mainly talk about Jupiter, and especially Jupiter's internal dynamics, with a focus on the zonal winds and on the magnetic field of Jupiter, in the light of the new data that have been gathered by recent satellite missions, especially the Juno mission. In the second part, I will briefly introduce the MHD model we developed to try to mimic some of the key features of Jupiter's internal dynamics. And then I will show you some selected results that are associated with these MHD models. So let me start my talk with some words on the Juno mission. So Juno is a NASA mission. So this is a NASA orbiter that started orbiting Jupiter in 2016. And so the original plan was to follow this orbit, which is shown in blue here. But because of some issues they had with some thrusters, they had to stay on an intermediate orbit, which is shown in green here. So this is a very elongated elliptical orbit, which goes very far into the magnetosphere, more than 100 times the Jovian radius, RJ, but which is also getting extremely close to the planet. And this is particularly useful if you want to gather accurate data from the magnetometer, for instance, which is on board Juno, or if you want also to have accurate gravity data that will help to better constrain the internal structure of Jupiter. And so this orbit is very long, so it takes more than 50 days. And so until now, a bit more than 30 orbits have been completed. And as I will show you later, those data already allow to build, for instance, or to construct magnetic field model with a much better accuracy than what was available before the mission. Okay, so the first aspect I will talk about today are the zonal winds, or the zonal flows that we observe on Jupiter's surface. So we observe these large banded structures that are associated with strong east-west winds that we call zonal winds or zonal jets. And they could be either eastward or prograde, as shown by these red arrows, or they could be westward, as shown here by these blue arrows. So now if you proceed to cloud tracking and accumulate statistics on the clouds, you're able to build some mean profile of the surface zonal winds for the 4 giant planets of our solar system. And that's what's shown here. So on the y-axis, you have latitude, and on the x-axis, you have the zonal flow amplitude in meters per second for the 4 giant planets. So on Saturn, you observe 2 lines, and they come from the global uncertainty on the mean rotation rate of Saturn, which is not known with an accuracy better than 5 minutes. And so it gives you an uncertainty on the way you have to define or recenter your mean flow. And so if we focus on Jupiter and Saturn, we observe a profile which shows a main prograde or eastward jet, which reaches around 100 meters per second on Jupiter and around 200 or 300 meters per second on Saturn. And this main jet at the equator is flanked by successively retrograde and prograde jet. And so we observe an alternating pattern of zonal jets which change their signs up to the polar regions. So one of the main questions with these jets that has been subject to a lot of publication until recently has been the concern with their depths. Is it only a shallow phenomenon that typically corresponds to the few tens of kilometers underneath the cloud deck? Or is it that do they penetrate deep into the molecular envelope of the planets, typically over thousands of kilometers? And so thanks to the Juno mission, gravity data have been gathered with very good accuracy. And what's shown here is the zonal gravity moment for Jupiter on the left and for Saturn on the right as a function of the spherical harmonic degree. So the blue circles corresponds to a model that has been constructed using the Juno data for Jupiter and the end of the Gastine mission data for Saturn. Now, if you look at this orange square for both planets. Those corresponds to the gravitational moment that you could construct by assuming that the planet is rotating as a solid body. And so for Jupiter, you kind of get a relatively good agreement until at least L equal 8. While for Saturn, you see a significant difference between the actual gravity moment and what you would get if you assume that the planet is rotating as a solid body. And the reason for that is that if you have zonal winds, they act, so it's differential rotation, it acts as on the mass distribution inside the planet. And so depending on the depth, it can more or less imprint onto the gravity signals. And so you can proceed as an inverse problem, and that is using the gravity data to infer the profile of the depth, or to better constrain the depth of the zonal winds. And so this is a non-unique procedure that requires additional assumptions on the way the jets will decrease or break at depth. So I just show you an example of such a procedure that has been done by Gastine and Gastine recently. So what's shown here is the average zonal flows as a function of depth in the northern hemisphere of Jupiter and Saturn. So in red, prograde jets, and in blue, retrograde jets. So we recover these alternating patterns, of course. And we see we can characterize typical depths for these jets coming from those models, which corresponds to roughly 3,000 kilometers below the surface for Jupiter, and something like 8,000 to 9,000 kilometers for Saturn. And so this is a non-unique procedure. So there is no consensus on the exact shape of the zonal winds at depth. But what makes sense, at least, is that there is a gravity signature associated with the jets. And so the depth of those jets is certainly not tens of kilometers, but rather thousands of kilometers. In addition to that, there is an additional constraint that comes from the observation of the magnetic field. So I will come back in a minute to that. But suppose the jets penetrate deep enough, you can expect that you will advect some magnetic feature because of the zonal jets just advecting your magnetic field feature. So if you are able to measure your magnetic field over a sufficiently large amount of time, then you can constrain the amplitude of the zonal jets at a depth of around 5% below the surface for Jupiter. And so this magnetic constraint gives you a typical zonal velocity of a centimeter per second at a depth around 5 to 6% below the Jovian surface. And so this is much weaker than the meter per second I was talking about when I showed you the profile of the zonal winds, which means that the jets are already broken by a factor of 100 when moving from the surface to 5% below the surface. Okay, so the second part I will talk about today is the magnetic field. So Juno has a magnetometer on board, and it goes very close to the surface. So from this vector magnetometer, you have measures of the three components of the magnetic field. And now if you accumulate enough orbits, you are able to construct the global magnetic field maps of the internal component of the field. And that's what's shown here. This is extracted from a very recent paper from Connerny et al. This is the radial component of the magnetic field at the surface of Jupiter using the first 32 orbits of the Juno mission. So this is a magnetic field map which is truncated to a spherical harmonic degree of 18, which makes it in terms of resolution actually quite comparable or even a bit more accurate to the geodynamo model or to the Earth's magnetic field model that we can construct. So what we observe here is mainly a dipole magnetic field, which is slightly tilted with respect to the rotation axis by around 10 degrees. And this dipole field is way larger than the Earth's surface field by a factor of around 30 to 40. So on top of that, it features some interesting localized magnetic flux concentrations, such as here in the northern hemisphere, or this so-called blue patch here in the southern hemisphere. It also features an interesting bit, which we don't see much at the surface, but which we'll see better when we extrapolate the field inward. Is this elongated east-west features, a magnetic field signature that we see in the equatorial region here, for instance, in the northern hemisphere. So now, if we proceed with the potential extrapolation of this field and extrapolate it up to the source or what we expect to be the source of the magnetic field. So on the Earth, that would correspond to the core mantle boundary. That's what's shown on the left. So this is the radial component of the magnetic field taken from the International Geomagnetic Reference Field at the core mantle boundary. While on the right, you have the Jovian magnetic field coming from the Connerny 21 model, downward continued 10% below the surface. So I'll come back to this choice of 10% later on, but what I can say already is that it more or less corresponds to the top of the metallic part of Jupiter where we expect the dynamo action to occur. So if we compare now these two figures, we observe, of course, still a dipolar structure on zeroth order, but on top of that, there are some key differences. So for instance, on the Earth, you observe this localized flux concentration in the equator, and also reverse polarity patches, like in the south, in the southern hemisphere. While on Jupiter, you also observe localized patches, so the blue patch here, for instance, but you also have a pronounced asymmetry between the northern hemisphere and the south. So on average, the magnetic field here is a bit stronger in the north as compared to the south. And we also see clearer now the features that show some pronounced alignment in the east-west direction in the equatorial regions. So the last questions about this field is the secular variation. So using the Juno data, people start to have a feeling on how the Jovian magnetic field could evolve with time by tracking, for instance, the advection or the evolution of these localized features, such as the blue patch. And so far, so the Connerny 21 model suggests that this feature has been advected eastward and would correspond to a zonal wind that should be, as I said before, around 1 centimeter per second, around 5 or 6% below the surface. So now, if we examine the internal structure or the expected internal structure of Jupiter, you get this kind of sketch where we have an external envelope which is filled by molecular hydrogen and helium, and then the pressure increasing downwards. We have a phase transition of hydrogens towards a metallic phase. And this phase transition occurs around 100 to 200 GPa, which corresponds roughly to 10% below the Jovian radius. And so that's why I took 10% beforehand. And so hydrogen becomes metallic. It reaches a level of electrical conductivity which is large enough to sustain a magnetic field via dynamo action. And so in between, there is this region where I put a question mark, and I put helium rain here, because some ab initio simulation of helium and hydrogen mixture in the range of pressure and temperature of Jupiter suggests that at this metallization front, helium gets immiscible with metallic hydrogen and forms droplets that just sinks downward. And so it's a little bit as if you would have a gradual enrichment of the inner parts in helium and like a lower helium rate in the external part. And so you form kind of a compositional gradient, which is stabilizing with the heavier an enrichment in heavier material downwards. And so you're in a situation of semi-convection with or maybe even in a regime of stable stratification. But I put a question mark here because there is no consensus on this. So this is very, I mean, this phenomenon is quite certain from ab initio models, but this is really on the edge of pressure and temperature values for Jupiter interior. So we don't know over what range of radius it happens. And so fully convecting models are still an option. And finally, in the inner region, you have a gradual enrichment of heavier material that we call, that astrophysicists call metal. So metal can be anything but hydrogen and helium. So so we have this diluted core, which is also quite uncertain, and we don't really know how it will impact the dynamics I will talk about later. But let's say on a zeroth order view, the classical picture is that you have jets that develop somewhere in this molecular envelope, and that the magnetic field of Jupiter is generated here in this metallic region. And so if we draw a second sketch, then you have convection everywhere, except maybe in this intermediate demixing region layer, where you could have either semi-convection or maybe stable stratification. And so here I kind of make the assumption that, well, this is molecular in this greenish region, and then suddenly it gets metallic in this inner part. But in practice, it's more intricate than that. And what I will show you just later is that the electrical conductivity rather increases smoothly. And so what you expect is rather a coupled dynamics between the external parts and the inner parts. And especially there could be a range of depth where the conductivity is not quite the value of metal, but is still sufficient to yield dynamo action, just simply because the level of turbulence in Jupiter allows to reach a fairly large magnetic Reynolds number. And so this is kind of the red dashed line that I put here on the sketch to just show you that there could be still some kind of induction or at maybe dynamo action even just at the very base of the what we call the molecular envelope. Okay, so what's shown here are two radial profiles coming from internal structure model from Martin French et al. So what's plotted on the left is density in kilogram per cubic meter versus radius normalized to the Jovian radius. And we see that the density increases by 3 to 4 order of magnitude in Jupiter. But maybe more interesting is the right panel, which shows the electrical conductivity as a function of radius. And so here again, we are not in a situation where the conductivity would be 0 in the molecular envelope, and then suddenly the value of a metal inside, but more in the situation where there is a gradual increase of this quantity. Okay, it's very sharp, but still it's continuous. And so it means that there is in between this transition layer where the conductivity is sufficient probably to already yield some induction or maybe some dynamo process. And so well, the takeaway message of this right figure is that probably what to be expected here is that we will get coupled dynamics between what's happening in the molecular part and what's going on in the metallic region. And so the main question we are interested in here, based on the observation of jets and magnetic field, is what are the physical processes that will sustain the jets, and where and how is the Jovian magnetic field produced? So to try to address these questions, we will develop some global, quotes, realistic models to try to put some constraints on the internal structure and dynamics of the gas giant planets. So that's what I'm going to present now. So we consider 3D spherical shell models under the magneto-hydrodynamics equation, so the MHD approximation. Practically, it means that we are considering spherical shells, which are bounded by an inner radius Ri and an outer radius Rho. And the fluid that fills the volume between these two spherical surfaces can be electrically conducting and can rotate to global rotation rate omega. And we can drive convective motion into this fluid volume by just, for instance, imposing a temperature contrast over the shell, or driving a volume or introducing a volumetric heat source and sinks, for instance. Instead of solving the full compressible equation, we make the anelastic approximation, so which means that we are filtering out all the fast acoustic waves, and then the momentum, so the density times the velocity u, is just a solenoidal quantity that you will be able to decompose into a poloidal and toroidal potential. So we then followed a pseudo-spectral approach that was introduced in the 80s by Gary Glatzmeyer. And so the numerical algorithm I'm using is still extremely close to the one put forward by Gary Glatzmeyer back then. And so to compute the simulation that I will present later on, I'm using the magic code, which is an open source code, so that you can download on this address shown here. So the MHD equation, they are governed by a certain number of dimensionless number, and four of them are really important. So the first one being the Ekman number, and this is the ratio of viscosity over Coriolis force. So if you consider, for instance, the liquid outer core of the Earth or the giant planet's interior, we are dealing with extremely low viscosity fluids, which have typically the viscosity of liquid water, but they're also subject to rapid rotation. So the Ekman number are super tiny, typically 10 to minus 15 for the Earth core. While in the numerics, because of the limited spatial and temporal resolution, you're bound to using much larger values, so typically 10 to minus 6 here. In contrast, the Radial number, which quantifies the vigor of the convective forcing, this is a huge number in turbulent astrophysical convection, so 10 to 30, for instance, for giant planets, while in numerics, you will be limited to much lower values, again, because of your limited turbulent levels that you can reach. So the Prandtl number, this is the ratio of viscosity to thermal diffusivity, and this is order 1 or 0.1-ish, so it's okay. While the last one, so the magnetic Prandtl number, this is the viscosity over the magnetic diffusivity, and for liquid metal or for metallic hydrogen, this is smallish, of the order 10 to minus 6 or 7. While in numerics, you're again limited to much larger values, so say 0.1-ish, or maybe a bit smaller if you do a good job. So the last one here, NRho, is well, has only to do with the reference states of the model. So this is only a measure of the number of density scale height your anelastic model will incorporate in the basic state. And so in the Earth core, which is a weakly compressible medium, this is a tiny number. So usually people put it to 0. While in giant planets, as I showed you, well, there is four orders of magnitude increase of the density. And so, well, you have to incorporate this ingredient, and in the numerics, you have to mitigate a little bit on this density contrast as well. So the last point I want to make here is about some diagnostic quantities. And one of them, which is very important, is the magnetic Reynolds number. So this is the ratio of induction of the field to the ohmic dissipation, or to magnetic diffusion of the magnetic field. And for the Earth core, this is, for instance, 1000, and this is a number that you can reach when you compute a 3D numerical model. And so this makes your life very easy when you want, for instance, to estimate the secular variation and connect what your numerical model produced to the actual data. But in Jupiter, unfortunately, the level of turbulence is much higher, and your magnetic Reynolds number is at least 10 to 5, maybe 10 to 6. And so you're really far off in terms of numerics. So that creates an additional complexity when you want to compare your models to the data. And so, well, the message here is that most of your control parameters are either under or overestimated by a large number of order of magnitudes. And so what you want to do is proceed by doing parameter studies and then try to derive scaling laws that can be possibly extrapolated to the planetary regime. Okay, I will now show you some selected results by first focusing only on models where we deal only with the molecular envelope. So there is no magnetic field, and we focus only on this layer shown in red on this sketch. And so what we learn already from models that are 15 years old now, this simulation by Moritz Heimpel, for instance, is that well, as soon as you consider 3D rotating convection models that are sufficiently rotating sufficiently fast, and where you consider turbulent convection, which is strong enough, then there is a tendency to build systems where you produce jets. and you produce jets that are not so far off compared to what's observed. That is, you observe a main prograde jet shown in red here, and then successively retrograde and prograde jets in blue and yellowish. And this alternated pattern is observed to the polar region. So I would say the first order properties or the first order observations are reproduced quite well by this kind of simulations. Of course, this simulation had the main drawback that it didn't include any effect related to the density variations. And but later, more recent models by Chris Jones and Kirill Kuzanian, for instance, or by myself, mainly showed that most of the results that were obtained in these Boussinesq models, they were maintained by, even if you would include the density contrast. And so as an example here, I show you a series of 5 simulations where the reduced ratio of the spherical shell more or less mimics the size of the molecular envelope of Saturn. And what is done here is that I decrease gradually the Ekman number, hoping to minimize the role played by viscosity. And especially if you look at the 2 rightmost cases, we observe jets, which are pretty much the same in those 2 cases, and which shown an alternating pattern with a prograde jet and in red, and then a retrograde, and then prograde. So we observe this alternating pattern, and we observe a solution that is not so much dependent on viscosity anymore. So that was also incorporating density contrast. So we were quite happy with this kind of results. So now, okay, so people were happy with this first series of models. So they say, okay, well, let's try to build the global models that will now also include the metallic part. And so now in this stage, the key ingredient you will incorporate is the variation of the electrical conductivity. So as I showed you in the introduction, this electrical conductivity increases sharply in this molecular envelope until this kind of dashed line where it reaches the value of a metal. And so you have the metallic region inside. And so people developed several of these models. So I will show you some of my results, but I insist that the results I will show are fairly robust, and people using different models more or less get the same kind of results that I will show. So here, this is a simulation that I conducted in 2014. So on the left panel is shown the zonal wind profile, so phi average U phi. In red, it's prograde, in blue, retrograde, and the dashed line corresponds to the part where it's getting metallic. And so we observe a main prograde jet, but nothing like alternating jets anymore at high latitudes. Now, if you look at the magnetic field produced by this model, so what's shown here is the axisymmetric toroidal field, color-coded in red and greenish, and the poloidal axisymmetric field lines showed by this dashed line here. And we observe 2 regions where the field is strong, basically at depth here, and close to the equator and close to the transition to the metallic part here. And an interesting aspect of this magnetic field was that it was fairly close to the Jupiter's magnetic field observed by the Juno mission. In particular, it very frequently produces this elongated structure east-west aligned in the equatorial region. So this was an interesting feature of this model, and we attributed this magnetic field features to the combination of 2 dynamo effects. So the first one being like a kind of a distributed dynamo over the convective metallic part. So this is a rapidly rotating system. So you build up a columnar convection structure and the helical flow. And these helical flows, they are prone to sustain large-scale dipolar magnetic field via what you could call an alpha square dynamo in the mean field naming convention. And so this part sustained the large-scale dipole. But on top of that, you see that just at the interface, or at the interface between the metallic part and the molecular envelope, the differential rotation is just scratching the very top of the metallic part. And so it's winding up the magnetic field lines there. a little bit similar to what's going on in the solar tachocline. And so you create locally some patches of relatively intense toroidal field. And so we argued at the time that in the end, those magnetic field features could be responsible from the variation and the appearance of this structure at low latitudes. And so we were quite happy with that. And again, well, this mechanism was found to be fairly robust in the sense that other models with different convective forcing or different details of the models found more or less the same. So this is what I say here. We produce Jupiter kind of like magnetic field in those global models, for instance, like similar to the models produced by Chris Jones in 2014. But the main drawback with these models are the jet structure. So on the left here, I show you again a hydro non-magnetic model with the zonal flow profile with the alternated zonal jets. And on the right, I show you the global magnetic model, which incorporates the electrical conductivity variation. And what we see is that, well, we are left with only one prograde jets and all the high latitude structure vanished. So does it mean that there is an extra physical process that is required to be able to get multiple jets at high latitudes? And so as I said in the introduction, one of the key ingredients that could be possibly missing is the stable stratification because of the immiscibility of helium with metallic hydrogen. And so this layer would be just in between or sandwiched or like intermediate between two convective layers. So the molecular part here and the dynamo region here. And in between, you would have a region where the mixing would happen. So as a kind of a primitive approach to that, I will just assume that it behaves as a stably stratified subadiabatic layer. So I will not include any double diffusive aspect here to model this layer. Okay. So to do that, what I do is that I simply consider a reference state where my entropy gradient is slightly superadiabatic in the molecule in the convective parts. So basically here and close to the surface, while it's changing sign, so it's getting subadiabatic in a thin layer in between those two convective parts. So of course, this is very simplistic, but at least the advantage of this approach that I can play with the thickness of the layer, and I can also play with the amplitude or the degree of stratification, which is characterized here in dimensionless units by the ratio of the Buhn-Weisser frequency n over the rotation rate. And so the simulation I will mainly focus on in the next slide is a configuration where this ratio is 5. So it's a fairly large degree of stratification. And then what's shown here on the right is the density again and the electrical conductivity in the numerical model we consider in orange, and from the ab initio calculation for Jupiter in blue. And the main point here to see is that because of the huge density contrast, we have to remove, say, the outermost 2% of the planet in our model to mitigate the density contrast, which otherwise creates really or leads to a very large variation of length scale of the convective flows. Okay, so we exclude this external 2% of Jupiter in our model. So what would be the effect of stable stratification on rotating convection? Here I took an illustration coming from Takeo and Lister from 2001. So they consider 3 configurations where they varied the level of stratification and Buhn-Weisser frequency over 2 omega. So with an increasing degree of stratification, so the part which is stably stratified here is the external region, while the inner one is convecting. And so what we see is that here your columnar structure cross everything, so they don't feel the stratification at all. But when the level of stratification gets large enough, then you start to confine your flow into the convective part. Furthermore, they derive a scaling relation for the distance of penetration of the convective feature into the upper stably stratified layer in this case. And they show that this distance is proportional to n over omega and proportional as well to L, L being the typical length scale of the convective eddies, which is impinging into the stable layer. Okay, so that's the first dynamical aspect you can expect here. And the second one, on the magnetic field, you expect that the stable layer will basically act as a skin effect on the magnetic field. So which means that well, a magnetic feature that has a time variability tau will be damped on a length scale delta, which is defined by this skin depth. And so since tau, the time variability of a magnetic feature of size L, is directly related to L over the typical velocity, then what you expect is that, well, everything that is varying fast will be small scale and will be filtered by skin effect. And so the main effect of a stable layer will be a low pass, kind of a low pass filtering of the magnetic field structure. So you will remove all the small scales and end up with a smoother field. So to illustrate the role played by this stable stratification, I just show you here an equatorial cut of the radial motion for a simulation where the stable stratification is defined between these two dashed lines here. And you have the dynamo region in the inner part and the molecular envelope in the external part. And you see that there is very little radial motion in between, meaning that most of the convective flow is actually well quenched by the degree of stratification we're imposing. We also observe a large scale separation between the dynamo region and the molecular envelope. And this, as I will show you just after, this is mainly related to the different leading order force balance that you have in those two fluid regions. Okay, an interesting aspect of this simulation is that it was conducted as quite extreme parameters in terms of what's possible numerically. And so we kind of reached a regime where in the end, we achieve decent energy separation. So what's shown on the left is the different components of the energies as a function of radius. So in blue, you have the magnetic energy, and in orange, the kinetic energy. So you see that at depth in the metallic part here, the magnetic energy is roughly an order of magnitude larger than the kinetic energy. So that's a good ingredient because that's typically what's expected. I mean, you expect even a higher separation in Jupiter, but at least you're on the right track regarding this ratio when you want to build a decent model for a planetary magnetic field. In contrast, if you look at the external regions, obviously the magnetic field amplitude decays because you're entering into a semi-conducting and then weakly conducting region. So the magnetic field amplitude decays. And then the kinetic energy rises. And if you look in details, this kinetic energy increase is mainly taken by the zonal motions, so the toroidal axis symmetric energy. So the dashed line almost perfectly match the full line. So which means that most of your energies in this outer layer is pumped into zonal motion. And again, that's an important ingredient of a decent Jupiter model, where you expect a very, very huge transfer of energy into the zonal motions. Now, if you look at the power source and sinks, which is shown on the right, so the buoyancy power versus radius is shown in green. So it's positive in the convective parts, and it's getting negative at the edges of the stable stratification part, and it's getting very close to zero in the very center of the stable stratified layer because you have almost no radial velocity there. So the ohmic dissipation is, as expected, strong in the metallic part, while it drops in the external weakly conducting region. And in contrast, the viscous dissipation takes over when the fluid is getting weakly conducting. So those ingredients also tell you that, again, in the metallic parts, we are quite happy about having most of the energy dissipated via ohmic dissipation and not viscously. So what we do afterwards is that we try to analyze the force balances of this model. And so to do that, we follow or we develop the different forces that enter the Navier-Stokes equation, and we build spectra of these different components. So what you see here on the y-axis is the magnitude of the different forces as a function on X of the spherical harmonic degree. So large scale are on the left of these diagrams and small scale are on the right of these diagrams. And so there are two panels, the left one corresponding to the metallic dynamo regions, while the right one corresponds to the external molecular envelope. So on both panels, what we see as leading order forces are these blue and green lines. And these blue and green lines here, or here, those are pressure and Coriolis. So you have a zeroth order balance between pressure and Coriolis force. This is called the geostrophic balance. And so this is expected for rapidly rotating system. So now if you can, of course, they don't perfectly match. So you can construct the difference between Coriolis and pressure and build what we call the ageostrophic Coriolis contribution. And this is plotted in gray here or here. You hardly see it because it's a little bit in the back. But what we see is that this ageostrophic Coriolis force is balanced on the large scale by buoyancy here in yellow, and it's balanced by Lorentz force on smaller scale, or say beyond a degree of 10 for the metallic part. And so here in the metallic region, this forms the so-called QG, so quasi-geostrophic Mach balance. So Mach being an acronym for magnetic, Archimedean, and Coriolis force. And this was an equilibrium that was devised theoretically by Peter Davidson in 2013. And so again, then inertia is an order of magnitude lower, and viscosity is 2 orders of magnitude below Lorentz force. So we again achieve kind of a decent force separation into this metallic part. Now, if you look at the external molecular part, we observe that Lorentz force drops quite a lot, and it makes full sense because the electrical conductivity is quite weakish there. And instead, the third forces that equilibrate the system is inertia, and so you end up with an inertia Archimedean Coriolis force 3 terms balance, which was also discussed quite a lot in the literature, for instance, by Gillet and Jones in 2006. And so we were also quite happy with this because the force hierarchy is reasonably close to what we believe is correct for the Jovian interior. Now, unfortunately, if we look at the magnetic field, we observe here, for instance, the radial component of the surface field. We observe a field which is dipolar, but which is way too dipolar as compared to the Jovian magnetic field. It lacks small scale features. It doesn't feature any more elongated structure. And so if we put that into a spectra of the surface field, you see that in orange, this is the numerical model here, time averaged. And in blue, this is the Jovian magnetic field taken from a Connerny, an older Connerny model. And you see that basically the ratio of the quadrupole to dipole or octupole to dipole is way too small in the numerics as compared to the actual observations or the actual models coming from the observations. And so that means that the field that is produced here is not very Jupiter-like. Okay, but there are also some positive aspects of this model, especially regarding the formation of jets. So what we see here are 4 simulations, the left one being entirely convecting, and then we incorporate a stably stratified layer, which is marked by those 2 dashed lines. And the degree of stratification increases, and we see that on the 2 rightmost cases, where the density stratification, or the level of stratification is larger than 1, then we start to form weakish kind of jets at mid-latitude, where we observe kind of retrograde and prograde and retrograde jets. Of course, they are quite weak. They are way too weak as compared to what you should get, but at least they start to emerge and form a system that is more reasonable as compared to the observation. So now, if you want to look at the force balance that is associated with those features and why are the jets maintained quenched at the edge of the stably stratified layer, what you basically do is that you consider 2 main balances. The first one being the vorticity balance, and especially the azimuthal component or the zonal component of the vorticity balance. And that's what's done here. So this is the curl of the Coriolis force. This is the curl of the buoyancy force. then the curl of the Lorentz force, and then the curl of Reynolds stress and inertial terms. So those two last bits are very tiny. And the main balance we recover is a balance between Coriolis and buoyancy. So we end up with the so-called thermal wind balance. And you see that in practice, the variation of the zonal flow along the axis of rotation Z is perfectly in balance with the lateral gradient of entropy. So in other words, the fact that you suddenly break the jets here with depth is accommodated by local intense entropy changes here. Okay, second balance that you can look at is simply the zonal component of the Navier-Stokes equation. So you phi average your Navier-Stokes equation, you end up with a Coriolis term that is directly linked with the meridional circulation. You get Lorentz force, Reynolds stress, and viscous stress. And here, what's interesting is that in the metallic part, we get a perfect match between Coriolis and Lorentz force. You see that the contours perfectly match here. While in the external region, it's quite intricate with some still sizable signature of Lorentz force at the bottom here, and also some major contribution of Reynolds stress as expected towards the surface. And so now if we zoom in as those two balances close to the transition, so we do a zoom over the stably stratified layer and a bit above it, we build up this diagram. So here you have the zonal flow profiles in the northern hemisphere, so between 50 and 90 degrees in latitude. And so we end up with these jets, and you see that those jets are indeed quenched fairly rapidly. So they change with depth quite quickly. And we also see that the thermal wind balance is perfectly realized. While on the lower panel, you see the meridional circulation and the balance between Coriolis and Lorentz force. So what is actually happening is that your Lorentz force prevents your meridional circulation to penetrate too deep into the stable layer. And so by doing that, your meridional circulation is weak, but is slightly accumulating local entropy variations with latitude. And because you have your thermal wind, then the jets have to be quenched as well with depth. Okay, so if I sum up, so we observe multiple jets on Jupiter. They are deep, at least 3,000 kilometers. Jupiter has a complex field. We have a fairly good resolution nowadays because of the Juno mission. We observe localized flux concentration, patches, also bands or equatorial elongated structure at low latitudes. We have reasonable asymmetry between northern and southern hemisphere. And the internal structure is still debated. We don't really know whether it's fully convecting, or actually we know it's not perfectly fully convecting, but we don't know whether there is helium demixing or not. And so is there kind of an intermediate stable layer, semi-convecting layer? So the numerical models, if I sum up in two sentences, the global models that are fully convecting, they produce a decent magnetic field structure that shares some properties that are observed in Jupiter, but they lack any multiple jets. And it's actually quite the opposite on the stable, on the cases that I just showed you, that incorporates an intermediate stable layer. Then your magnetic field structure is too simplistic, too dipolar, but you start to produce kind of mid-latitude multiple jets. And so at this stage, we don't really know what could be a possible way to improve the models, possibly make it thinner to mitigate the skin effects. Make it closer to the surface as well. So just lift everything a little bit upwards to get a little bit less damping of the magnetic field. That could be also an alternative scenario. Or maybe we need another or an alternative scenario to break the jets at depth. And so we don't know. And with that, well, I thank you for your attention.